Hi everybody, and in this lecture we're going to cover the topic of what's called motional EMF, right? So motional EMF is when you create a voltage in a closed loop of some type by moving that object through a magnetic field. Okay. Now the magnetic field can be static or it can be changing. It doesn't matter. Because remember, all that matters is as long as there is a change in the flux. Now it could happen that you move something away from a magnetic field and increase the strength of the magnetic field at the same time, and do so in just the right rates that they cancel each other out, as long as part of the object is in the magnetic field. But we're not going to worry about that particular circumstance here. For this example, we will suppose that the magnetic field is constant. Okay. Now we haven't assigned it a value yet. We will assign that value here shortly. But for the moment, just imagine that I have a uniform magnetic field into the board, okay, and I have a loop of wire here, and it's in a rectangular loop, and one side has length B and the other side has length A, and I'm going to pull the wire out with a velocity V. Okay, now what's going to happen? Well, especially in the case where the magnetic field is constant, what's going to happen is the flux through this area is going to change as we pull the loop away from the magnetic field. Okay, so how can we describe this? Well, remember that the voltage induced in the wire is going to be equal to the change in the flux, right? So this is just Faraday's law, and the minus sign gives us Lenz's law, okay? So the voltage is going to be equal to the rate of change of the magnetic flux with respect to time. Now, how do we describe the magnetic flux, right? So the magnetic flux the magnetic field is going to be into the board, and because the rectangle, the loop, is planar with the board, that means its vector direction is either going to be considered to be out of the board or into the board. And so remember that the magnetic flux is defined as B dot A, where A is your area. And so this just turns into BA cosine theta, okay? But we can consider the directions to be parallel, right? The magnetic field is into the board, and the area we can consider into the board. And so the cosine of theta goes to 1, cosine of 0 is 1. So we can say that the flux then reduces to just BA. But the area of the loop is A times B, okay? So this is the magnetic flux. But, okay, what happens when the loop starts to leave the field? Okay, what happens when the loop starts to leave the field? Well, if this is the boundary of the field, okay, then the area that is capturing this flux, we can think of this as a length of x. Okay, so not an x as a magnetic field into the board, but x the variable, okay? So I'm going to label this length x right here, the part that is still in the field, right? So this is technically the area is going to be b times x. Okay? And as I pull the loop outward, x is going to get smaller. Okay? X is going to get smaller. And as x gets smaller, the part of the loop that's in the magnetic field, more of your loop is going to be external to the field, and your overall flux is going to be decreasing. Okay? Now, here, this is the expression that we can insert into Faraday's law, and this is going to give us negative d dt of the magnetic field times the area of the loop that's still in the magnetic field. And if my magnetic field is constant, then this isn't changing. And this length, or this side of my loop, is not changing. And so b is a constant, lowercase b is a constant, but x is the variable that's changing, right? So x is going to be getting smaller. And so these first two factors are going to come out of the derivative. So we're going to get negative capital B times b times dx dt. Okay? But what is dx dt? Dx dt is just the rate that the loop is being pulled out of the field with. So this is going to be negative b times v, and technically the negative sign goes away because dx dt is a negative quantity. Dx is getting smaller. And so that negative sign is going to cancel with the Lenz's law sign, and my result is just going to be the strength of the magnetic field times the dimension of the loop that is not changing with respect to the field, times the speed that you pull the loop of wire out of the field with. And a lot of books define this to be L, and so they will write this as BLV. It doesn't matter what you call this, it just is what it is, right? Whatever this dimension is going to stay constant. And if you have a resistor in here, or if you know the internal resistance of your wires, then you can calculate what the current would be, because the current would be equal to Ohm's law, or it could be found from Ohm's law, and I would then be the induced voltage divided by the resistance, or this would be BLV over R, okay? And as long as the rate that you're pulling the loop with is constant, and the magnetic field is constant, in other words, as long as the rate at which the flux changes is constant, then the current will be constant. Once the loop is completely out of the field, that will change. And if you're pulling the loop through the field before the loop exits the field, before this tip would exit the field, you wouldn't have any current. But as soon as this tip goes past the region where the field has influence, and you're pulling the loop this way, as long as that condition is holding, you will observe this current. Okay? That is the current that you will see. So that is motional EMF. And the way to find motional EMF, the recipe is very simple. Start with Faraday's law. Understand what your magnetic field is. It'll usually be given to you. It will either be a function of time. At our level, it usually won't be a function of position. And in most cases, it'll be constant. figure out what your area is, figure out what area is being influenced by the magnetic field. That gets you your flux, take the derivative, and you've got the induced electric field. I'm sorry, the induced voltage, okay? The electric field is what I'm going to talk about here in just a moment. Once you have the induced voltage, you can then talk about the induced currents if you know things about the resistances that are present in your system, okay? So, with that in mind, let me talk about the voltage real quick. So remember that the induced, we don't have to worry about induced quantities just yet. Let's just go back to the definition of voltage from some chapters ago. Remember, the definition of voltage is the negative line integral of the electric field dotted into a path, okay? And technically, this is the change in potential, okay? So your change in potential is going to be equal to your electric field dotted into a path with the negative sign here. We can connect this with Faraday's law because your induced voltage plays the same role as this quantity does, right? Your induced voltage plays the same quantity as your potential difference in from, say, a battery or from moving charges around in electric fields. And so we've got E is equal to negative E dot dl, but that also equals Faraday's law, and the negative signs cancel out. And so what we can say is, and this is magnetic flux, not to be confused with electric flux. And so what we can say is the path integral of the electric field is equal to the time derivative of a flux. Okay? So the path integral of my electric field is going to be equal to the time derivative of my flux, all right? But what does this look like, right? What happens here, all right? Well, what happens here is that your line integral, okay, for voltage to cause charges to flow, you have to have essentially, especially when you're talking about charges flowing through wires and such, you have to have a complete circuit. The way to have a complete circuit is that this has to be a closed integral. You have to complete a path. You have to go through a complete path. So this has to be a closed integral. You have to at least end up where you started from, if not go beyond it. But the closed path just means you come back to where you started from, right? So as long as you go around a closed path, but the only way you can go around a closed path, okay? The only way you can go around a closed path is at some point if you go in a circular motion, right? The only way you can do that is if you go in a circular motion. The induced electric fields from Faraday's law, the induced electric fields, not the potential, but the induced electric fields that a changing magnetic field causes, okay? And by the way, this is the third equation of Maxwell's equations. We've already seen two, and we'll sum those up here in a minute. But the point to drive home here is this quantity right here represents a change in the magnetic flux with respect to time. That change in the magnetic flux, usually due to a change in the magnetic field, induces an electric field. And that electric field will be circular, okay? That electric field will wrap around the changing magnetic field. This shouldn't be too surprising. we've already seen something analogous to this with currents and wires producing a magnetic field. When I have a voltage in a wire, if I have a straight wire and I have a voltage in that wire and current is flowing through it and flowing in a straight line, the magnetic field wraps around it. If I have a magnetic field pointed in a straight line up or down, now in this case the magnetic field has to be changing. But as long as it is, it will cause electric fields to wrap around it. Okay, so this is going to be circular types of electric fields, and they will wrap themselves around the magnetic fields. Okay, they will wrap themselves around the magnetic fields. So one way to visualize this, right? One way to visualize this is to look at a solenoid. So, and actually, let's just look at a single loop of wire. Okay, we won't go through the whole solenoid case, but let's just go through a single loop of wire. Let's start with the single loop of wire, and then we'll go to the solenoid. Okay, so here we go. If I have a magnetic field, and let's say the magnetic field is pointing this way, and I have a loop of wire that looks like this, okay? And if my magnetic field is equal to I don't even care what it is. Let's make it an exponential decay function. So it has some initial value, and that'll exponentially decay with some law. And if this is the case, right, if my magnetic field that is piercing through this coil is going to change with respect to time, then there will be a current induced in the coil, right? Now, how much and in what direction? Okay, well, first things first, let's go ahead and assume that the coil has internal resistance R. Okay, so my coil has internal resistance R. And under that condition, right, it also is, we need to have the, we will call the radius of the loop A, right? We'll call the radius of the loop lowercase a. So then the area of the loop is going to be pi a squared, right? I suppose I could have used lowercase r, but it doesn't matter, right? So now what we want to do is we want to calculate what the value of the electric field is going to be, right? So we can both calculate the current and we can calculate the value of the electric field, so we'll do both. But first things first, to find the current and B, the electric field, okay? To find these two quantities, we have to start with Faraday's law, right? So we're going to start with Faraday's law. And remember that Ohm's law, to solve part A, we just did this, but just to formalize it down, remember that part A, to solve for the current, is going to be the voltage divided by the resistance. But the voltage is going to be found from Faraday's law. And the flux, again, magnetic flux, If the coil is not moving, if the circular loop of wire is not moving, then the change in flux is going to be strictly due to the decay in the magnetic field. Now, what direction, before we go any further, what direction does Lenz's law imply the induced current will be? Well, the magnetic field is pointing this way. It's decreasing. So the change in your magnetic field is actually this way. So your coil is going to want to induce a current such that it produces a magnetic field this way through the loop. So if this is the, let's say that this side is the near side of the loop and it curls into the board and then comes back out. In that case, if I want magnetic field to come up this way, then my current is going to flow this way, right? So my current is going to flow this way. And my magnetic field, I'm running out of colors here, but we'll use black. Then in that case, the magnetic field is going to do something like this. And all of these will wrap around. And you would get a magnetic field that looks like that. And so the magnetic field is going to be pointing in this way, and that requires a current flowing like this, right? So now what is it? So to find the current, or to find the current, we need to find the voltage. This is going to be negative d dt of, the flux is going to be B naught e to the negative alpha t. And alpha is just a number, okay? Alpha just dictates the rate at which the exponential function decays, okay? So alpha is just a number. Times the area pi a squared. This is constant and this is constant. So the only thing that gets differentiated is going to be this. So this is going to be equal to B naught pi a squared. Then so this is the constant part. Then I differentiate the exponential. This is going to be negative alpha times e to the negative alpha t. Okay? And the negative sign from Lenz's law cancels with the negative sign brought down from the differentiation. So we've got that. And so then the current is going to be all of this divided by R. Okay? So my current is all of this divided by R. Right? Now, what about the electric field? Okay? Well, the electric field E dot dl is going to equal this over times R. So it's going to equal this, right? So it's going to equal B naught pi a squared times alpha times e to the negative alpha t. Right? And since this is a closed loop and the electric field will effectively be constant through this closed loop, which it must, we can take e out of the integral, and the line integral through the loop is just the circumference of the loop, So this is very akin to Ampere's law. So this is going to be E times 2 pi times A is equal to B naught pi A squared alpha e to the negative alpha t, right? And my pi is going to cancel out. I'm going to cancel one of my A's, and I'm going to have a factor of 2 on this side. So this is going to be E times, or E is going to be equal to BA alpha e to the negative alpha t all over 2. And this is going to be in the rotational direction. In cylindrical coordinates, we would call this the phi direction, but it's going to be circular, okay? And it stems from the fact that this has to be a closed loop to induce a current in a loop, okay? If you don't have a closed loop for which your current to flow, you will not induce any current. So, because it has to be circular, your electric field will be circular. Okay, that's what I'm really trying to drive home here. When you have linear magnetic field that's changing, it will induce circular electric field. When you have a linear electric field that's producing a current, it will induce a circular magnetic field. Right? So that is the point that we want to drive home. So that is Faraday's law. That is how it connects to the electric field. And you could actually calculate, okay, if you wanted to from here, you could calculate the magnetic field that is induced inside the coil. We already know how to do that. We have to be along the axis, right? We would be able to calculate the magnetic field at some point along this axis. But if you remember, we did that calculation from the Biot-Savart law. So that would tell you how much magnetic field is induced from the current that got induced. So the changing magnetic field here, there's a lot going on. Your changing magnetic field here causes a change in the flux through the wire, through the loop. Because you experience a change in that flux, you're going to induce a voltage. If current can flow through that wire, it will, and it will flow through that wire according to Ohm's law. And because current then starts to flow, it creates its own magnetic field. And this is the point of Lenz's law. That magnetic field wants to oppose the change in the magnetic field, or the change in the flux up here. So if my magnetic field is decreasing and getting smaller, it's going to want to create a magnetic field in the same direction that the original magnetic field was pointing. If this were not a negative sign, if this were a positive sign and my field were growing, then my induced magnetic field inside the coil would be in the opposite direction. And these arrows would be pointing out this way, right? Because the field would be growing, the induced current would try to oppose that change, okay? So that is how Lenz's law, Faraday's law, all connect with how voltage is described from earlier electrostatic consequences. And let me, before we go, say just a couple of things about Maxwell's equations. Now, we've already seen two of them, right? We've already seen two of Maxwell's equations. We have Gauss's law. And Gauss's law tells us what the electric flux through a surface is if I know how much charge is enclosing that surface, okay? That is what Gauss's law is telling us. I can calculate the flux if I know the amount of charge, Okay, now we need to be very, very careful. It does not tell you how much charge is in a region and how much electric field is in a region. It says you can calculate the flux through a surface if your surface is enclosing a charge. And it might actually be beneficial to spend some time on this, because this is actually something that it took me a while to kind of sort through and sift through. So let me give you an example. Imagine I have a couple of charges, maybe 3 charges. Call this Q1, Q2, and Q3. They're not necessarily all the same. Okay, they're not necessarily all the same. What Gauss's law doesn't say is that if I draw a Gaussian surface around one of these charges, okay, if I draw a Gaussian surface around one of these charges, let's say that this is a Gaussian sphere, what Gauss's law does not say, okay, is that I can ignore the electric fields from all other contributions, okay? So these 2 charges are definitely going to be giving off electric fields, right? What Gauss's law tells us is that I can calculate what the flux is if I know how much charge is enclosed. So here's what we're saying. We can calculate the electric field due to Q1. And let's say that all of these are positive, okay? So Q1 is going to have some outward directed lines here. And all Gauss's law says is if I know what charge is enclosed, I will be able to actually calculate what this flux is. And conversely, if I can calculate the flux, I can calculate what the charge enclosed is. So it's a very powerful tool. If I know one, I can get the other. If I know the other, I can get the one. But these charges out here are still giving off electric fields, no doubt. But these don't contribute to the calculation, because for every field line that pierces one part of the surface, it has to exit at a different part of the surface. So there's no net contribution from an external charge. Okay? So if you want to get the total electric field in a region, you have to enclose all of the charge in that region, right? If you want to get the total electric field, now you can enclose them with different Gaussian surfaces. You don't have to take one giant Gaussian surface. You can take 3 different Gaussian surfaces and calculate the flux through each of those, and then you have to add those fields together once they're all 3 calculated at any given point in space. But just because I draw a Gaussian surface around one of them does not mean that the electric field contributions from the other charges are negligible. It simply means that through my Gaussian surface that I've specified, if I have charges outside that region, they don't contribute to any of the flux, because anything that goes into that surface has to then exit the surface at some other point. So no external charges contribute to the flux. That's why you have to enclose the charge. Okay, so that is the first of Maxwell's equations. The second of Maxwell's equations is the Gauss's law for magnetism, which says that we don't have any monopoles. There is no such thing as a magnetic charge that will give off loops that, when they penetrate a Gaussian surface, wouldn't then close back in on themselves. So the reason that this is 0 is because if I have a magnetic object, right, and I draw a surface around that object, let's say I draw a sphere around that object, if this object is magnetized, every single magnet that we've ever observed here on the Earth does this. So even if I have a field line exiting my surface here and exiting my surface here, those same field lines are penetrating the surface back at those points down there. And so again, that just simply means that there is no net flux. For every field line that exits my surface, another field line has to come back and enter the surface. And so I won't have any net flux. That's why this is zero. That is Gauss's law for magnetism. And Faraday's law is the third of Maxwell's equations, and it's usually going to be written like this. And you'll notice this is why we wanted to connect with the closed loop integral form, because the closed loop of the electric field is going to equal the time derivative of the magnetic flux. And we've already seen half of Maxwell's fourth equation. And you might even start to notice the pattern. E dot something, B dot something, E dot something, and the fourth of Maxwell's equations is Ampere's law, which says B dot something. Well, in the first two, it was B dot dA. In the last two, it's E and B dot dL. Okay, so it's nice and symmetric. There's a nice symmetric pattern here. But Ampere's law, as we understand it right now, just simply says mu naught I. Okay. What Maxwell did, Maxwell fixed this, and you'll notice that this is where the symmetry is broken on this side, right, between here and here. Here, this is just saying we can calculate the electric field if we know the charge enclosed. There is no such thing as a magnetic monopole. But to kind of preserve the symmetry that we see on this side, you have to do something, right? And so this was what Maxwell did. This is what Maxwell did. He reasoned, okay, and we'll talk about this in the next chapter, but he reasoned if changing magnetic fields produce electric fields, what if not just current produced a magnetic field, but what if a changing electric field produced a magnetic field? And in fact, it does. So there will be a term here that is very analogous to this, that says if I have a changing electric flux, and that electric flux, or if that flux is changing with time, then I will also induce a magnetic field. But that breaks the symmetry even further, right? So without writing out the constants out front, we will have a term that looks like this. Okay? We will have a term that looks like this. This is one of the greatest pieces of mathematical machinery in all of physics, okay? Maxwell's equations. Because the symmetry outlined here is very, very striking. My electric fields and my magnetic fields each can be described in terms of how you integrate them over a surface or a line. And I can talk about how the charges are going to behave. Now, this is what this equation is saying in terms of quote unquote charge. I can calculate the electric charge from the flux, if I know the flux, or I can calculate the flux from the charge. And there is no such thing as a magnetic charge. If there were, then that would be what we call the so-called magnetic monopoles. This is current, or the flow of electric charge. This is a change in the electric flux. This is a change in the magnetic flux. It would stand to reason, if we ever find magnetic monopoles, we would find a term here that would be analogous to electric charge. It would be a magnetic charge. Or if I can cause magnetic charges, magnetic monopoles, to flow through space, that would be a magnetic current. And then I would have a term here, and we would predict, based on this symmetry, that if I could produce a magnetic current, that would then induce an electric field just the same way that a changing magnetic field does. Okay? So current is due to moving charges, which are due to an electric field. So either way here, you're not getting away from the electric field. What you're basically saying is, in some mechanism, an electric field is responsible for creating a magnetic field. And we would expect the same thing up here. We would say if some mechanism, be it a changing magnetic field or the flow of magnetic charge, would be responsible for the electric field. Okay? So that's a bit about Maxwell's equations. That's why we love this symmetry and why the magnetic monopole problem is so important. It's worth an automatic Nobel Prize. So if you can go find a magnetic monopole, you will automatically get a Nobel Prize. And there are different methods that some people have for looking for them. We haven't found any yet, but this is the symmetry that Maxwell's equations have in them already and would have in them even further if we were able to find such a particle. All right. So in the next video, we will start AC circuits and talk about electromagnetic waves. And we will see you then. All right.